This is the second video of projectile motion. So we're going to talk about the second type of projectile motion, and I've diagrammed that here. In this type of projectile motion, the object starts off on the ground with a velocity which is slightly upwards and slightly horizontal. So it has both an x and a y component. And the object travels up, slows down due to gravity, and then accelerates downwards, speeding up, and comes back to the ground. So again, you can see the two distinct motions. In the x direction, horizontal motion, horizontally uniform motion, and in the y direction, vertical accelerated motion. So you can see on the way up, it's accelerating in slowing down in terms of the speed. So it's going from a very high vertical speed down to 0 at the top, and then on the way down, it's accelerating, speeding up, and the speed is increasing. So again, we want to find the horizontal displacement or the range. How far does it travel in the x direction? So let's assume that it starts off traveling with an initial speed of 10 meters per second, and that's at an angle of, let's say, 53 degrees above horizontal. Okay. So that would be this vector here, 10 meters per second at 53 degrees. And we want to find the range, the horizontal displacement. So again, let me just make our diagram a little bit smaller so we have some room to work. In the x direction, we know dx is equal to vx times t. It's uniform motion. In the y direction, this time it's the vertical displacement that is 0. It starts off on the ground and it ends up on the ground. So in terms of displacement, remember displacement is how far is it from where it started. In the y direction, it doesn't appear to have moved. It's here at this vertical position at the beginning and at the end. So when we look at the vertical motion, in this equation, it's the left-hand side which is 0. So we have 0 is equal to the initial y component. So again, it's traveling at 10 meters per second. And the y component would be the opposite side of the triangle. So I need to add in sine of 53. So that's my initial y component. And I'm going to multiply that by the time. And then I want to add in that it accelerates downwards due to gravity. And multiply that by the time squared. Now you'll notice I have time in both of these terms, but because it's set equal to 0, I can divide through by time, and I can cancel one of the times out of each term. And obviously 0 divided by time is still 0. So what I end up with is that the time is going to be equal to 2 times 10 times sine of 53 divided by 9.8. And we end up with a time of 1.63 seconds. Okay, so again, that is the time that it takes to complete this motion from here upwards and downwards, 1.63 seconds. So the horizontal displacement, dx, the range, is going to be the x component of the velocity, so in this case 10 times cosine of 53, it's the adjacent side. Multiply that by the 1.63 seconds. So we end up with a range of 9.8 meters. Now, Again, we can also be asked what is the final velocity, the velocity that it has when it strikes the ground over here. Now it should be obvious from our diagram that it has the same velocity that it starts off with. It should be 10 meters per second. The only thing that changes is the direction. When it started, it was traveling at 53 degrees above the horizontal. Now it should be traveling at 53 degrees below the horizontal. Let's go through and actually prove that though. So let's find first the final y component to the velocity. So again, to find that, I know that vy is going to be equal to the initial component plus a times t. And I know that it starts off traveling at 10 times sine of 53, and then it accelerates downwards for 1.63 seconds. So the final y component to this velocity is negative 8 meters per second. And the x component is 10 times cosine of 53. And that works out to be 6 meters per second. So the final velocity, which will be the square root of those two components squared, when I square 8, I get 64 plus 36, that's 100. The square root of 100 is 10 meters per second, right? That's the same initial velocity that we had. And if I look at the direction, again, I'm looking for the tangent of that angle. And again, the angle that we're interested in is the angle here, the angle below the horizontal. And it's composed up of an x component here and a y component. So the opposite side is the y component, which is 8, and the adjacent side is the x component, which is 6. And that angle, again, works out to be 53 degrees. So the velocity that it has at the end of its motion is the same velocity that it had at the beginning of the motion. The only thing that's different is the direction. Here it was traveling upwards from this direction. Now it's traveling downwards at the end. And that's the second type of projectile motion.